this is Gigi from Kauai Community College. This is a lesson on continuity. So loosely, we know the definition of continuity is that we can draw a graph from start to finish without lifting up our pencil, right? So like this, if you have, here's A, here's B, and if we were talking about the interval from A to B, we're saying, well, if I could draw the function from A to B without lifting up my pencil, then it's continuous. Okay, so let's look at when it's not the case. Okay, so here are some examples of functions that are not continuous and the type of discontinuity. Okay, so types of discontinuity is what we call these. So the first one is a hole, right? So you have a hole at x equal to 3. X equal to a here, okay? And this right here is a removable discontinuity because all we gotta do is just say, hey, it's an easy fix. If I just fill in the hole, then it's continuous, right? And then the second one is an infinite discontinuity, like an asymptote. Okay, this is not removable. Okay, so not removable, meaning it's not a thing that you can fix. Okay, and then here we have a jump where you start the function from here and then you have to actually lift up your pen and go down to finish up the other branch, and that is a jump, and this is not removable. Okay, it's not an easy fix. And then the next one, wait a minute, couldn't you just draw this graph without lifting up your pencil? So why is this a discontinuity? Why is that? Well, this is when the loosely used definitions need to be formalized, and we need to talk about the formal definition of continuity. Okay, so what is it? What does it mean mathematically? How do we define continuity? Besides the fact that we can wave our hands and say, oh, if you can draw without lifting up your pencil. Well, here's the definition. The function f of x is continuous at a point C in its domain if the limit, okay, so here is like one equation that defines what it means to be continuous. If the limit at x go to c of f of x is equal to f of c. So this is a very loaded equation. That equation translates to these criteria needing to happen. One is that you must have a function value at c. Okay, meaning c must be in the domain of the function. Okay, and then the second condition must be, well, there has to be a limit when x approaches c. And then third, then you would say that limit now must be the same as the function value. That's the third condition. Okay, so one equation definition, limit at f of x as x approaches c is equal to f of c. But what it means for us to actually go through the criteria to check to see if the function is continuous or not is to check 3 conditions. Is there a function value at c? Is there a limit as x approaches c? And then is that limit the same as the function value? Now note that if we are at the endpoint, then we are talking about the limit as x goes to c from the right or from the left, meaning one-sided limit of f of x is equal to f of c. Okay, we're talking about one-sided limit if we are at the endpoint. Okay, so if a function is continuous for all points in its domain, then we would say the function is continuous over its domain. Or if the function is continuous for all points over the set of real numbers, then we would say it's continuous over the set of real numbers. Or if it's continuous over an interval, then we'll say it's continuous over an interval. Okay, so we have to say when it is continuous. Is it over its natural domain? Is it over a closed interval? Or is it over a set of all real numbers? Okay, so let's take a look at these examples and say why. Which of those conditions fail? Okay, so when we look at this right here, the first condition is, in this case, we're using A instead of C. But we would say f of A does not exist. That condition failed. Okay. However, there's the limit as x goes to a of f of x is that point right there. Wherever that hole is. Okay. So let's call that value L. Okay, that equal to L. There's a limit. Okay, now we need this, in order for it to be continuous, we would say the limit at f of x has to equal to f of a. In this case, if we can make it equal to L, then it can be fixed. So that's what we mean by removable. This can be fixed. If there's a limit, we can assign the function value to be whatever the limit is, and it can be, the discontinuity can be removable. Okay, now, in the second scenario, which one of those conditions fail? Well, there's no f of a. F of a doesn't exist, right? And then the limit doesn't exist. Well, if the limit doesn't exist, I cannot assign the limit to be a function value. So it's definitely not fixable. And why is this limit not existing? Because approaching from a, from the left, right? Limit as x goes to a from the left of f of x is infinity, whereas limit as x goes to a from the right of f of x is negative infinity. Not the same. So the limit doesn't exist. Okay, so the limit doesn't exist. And that is what we call an infinite discontinuity, and it's not removable. There's no limit to be assigned to a value. Okay, here, a jump, discontinuity. Well, as we can see, limit as x goes to a from the left, it is going to equal to this value L. Whereas the limit as x goes to a from the right of f of x, it is equal to whatever that number is. I'm going to call that m. Well, these are obviously two different numbers, right? So here we would say, yes, there's an f of a. However, the limit as x goes to a of f of x does not exist. There's no limit because approaching from the left, it goes to one number. Approaching from the right, it goes to another number. And if there's no limit, I cannot assign that limit to be a function value. Therefore, it is not removable. Okay, as far as oscillating go, which condition fail? Well, there's a function value everywhere. Okay, and that's why we say when we were using that lose definition, we're like, okay, I can actually go ahead and not lift my pencil here. But what happened? The limit at x goes to a of f of x, that does not exist because your function value bounces up and down, up and down, up and down. So going from the left, it goes to one number, it goes from the right, it goes to another number, and there is no limit. So oscillating discontinuity is also not removable. So the only one that we can say can be removable if there was a hole. Okay, so let's take a look at some functions here. Suppose you have the function square root of 4 minus x squared. Well, if you could see that in your head and know that the domain is from -2 to 2, that's great. Now, if not, how do we find a domain? Well, looking at this thing inside the square root, because that has to be 0 or higher. Otherwise, I cannot take the square root. So 4 minus x squared needs to be greater than or equal to 0. And so in order to find out that solution of an inequality, we'll go ahead and find out the cutoff points, meaning when is 4 minus x squared equal to 0. So for x, we will have plus or minus 2. If we put that on a number line, those are our cutoff points. -2 and 2. And then we're going to test to see what works. If you pick a number to the left, say -3, 4 minus x squared is going to be -5, which is a negative number, and you cannot take square root of a negative number, so that doesn't work. And then if you pick 0, oh, that's okay. It's 4, it's a positive number. So that part right there is okay. That belongs to the function, all of those x values. And then if you pick a number to the right of 2, let's say 3, you'll get a negative number again, and you cannot take square root of a negative number, so that doesn't work. Therefore, the domain is -2 to 2, and if you look at it, it is half a circle. So with all the points in its domain, we can say that there's f of c everywhere in its domain, and that there's a limit everywhere in its domain, and that the limit is the function value. I mean, really, pick any c, right? Let's say -1 right here. We can tell that approaching from the left and from the right, that the limit of f of x as x go to -1 is f of -1. Now, what about the endpoint? At the endpoint, we are talking about the limit as x goes to -2 from the right of f of x, and that is equal to f of -2. Or on the right, we are talking about the limit as x go to 2 from the left of f of x, and that is equal to f of 2, which is 0. So this function is continuous everywhere in its domain. Okay, so we can say f of x is continuous over its domain. Or we will say that domain is a closed interval from -2 to 2. Oh, closed interval, not open, closed. Okay, now let's take a look at this. Well, first, what is the domain? It looks like -1 to 0, open, and then 0 to 1. And then we are going to include 1 somewhere. So right here, okay, we could have combined the interval to be from 0 to 2 because 1 is included. So the domain is from -1 to 0, union 0 to 2, union 2 to 3. Okay, that U may look like a V, U. So 1 is within the domain. So when looking at the graph over its domain, you would see something like this. Now it depends. If we're talking about over the domain, then 0 is not in the domain. So we don't need to worry about that. However, 1 is in its domain. So there's discontinuity at x equals 1. Now, is this removable? I say yes. Move this up. And that is removable. If we could move that up. And then this right here and that right here are not in its domain. So as far as over its domain go, there is only one point of discontinuity at x equal to -1, and it's removable by assigning the value to be, say in this case, 2. If you say that is 2, then it will be continuous over its domain. Okay, now if we're talking about the function being continuous over, say, the interval from -1 to 3. If we're talking about the interval from here to here, then we have more points of discontinuity. Okay, does that make sense? We would say here we have discontinuity at x equals 0, -1, 2, and 3. But over its domain, because these other points are not in the domain, we don't count them. Okay, so really when we're talking about continuity, are we talking about a point inside its domain? Are we talking about over some interval, right? So pay attention to that. Here's the function. And when you see functions like this, you would say, oh, hey, look, I can factor out the denominator. And when x is not -1, I can go ahead and divide out x plus 1. And so it can be simplified to just 1 over x minus 3. Well, be really careful. It is 1 over x minus 3 with a whole at -1 and 1/4 or -1/4, because the only way you could have simplified was if x is not -1 when you're not dividing by 0. Okay, so then the domain of this function is negative. Oh no, that's not it. One more branch, union 3 to infinity. Okay, so everything except for -1 and -3. So when you graph this, you would say, oh, look, you know, over this domain, my graph looks like this. There's a hole at -1, -1/4. Okay, so this function is actually continuous over its domain. However, if we were talking about over a set of real numbers, we have a removable discontinuity right here, and we have an infinite discontinuity right there. Okay, so really we need to distinguish when we're talking about continuity. Are we talking about continuity over its domain, or are we talking about over some interval, arbitrary interval, right? Most of the time we are interested in continuity over its natural domain because really we only should be operating within the domain of the function. Okay, so here is an abstract question to summarize whether or not you know what it means to be continuous. Okay, so in order for the function to be continuous at x equal to 1, the one sentence definition would be the limit as x go to 1 of f of x must be equal to f of 1. Okay, so in order for it to be continuous, this must happen. So if we look at this here, we would say limit as x go to 1 from the left-hand side of f of x. Well, approaching from the left, I'm talking about the top branch there. And we're talking about the limit as x go to 1 from the left of 2x squared minus 1. And if we plug in the 1, we would get 1 squared is 1 times 2 is 2 minus 1 is 1. So in order for this to be continuous, there must be a limit. So the limit as x go to 1 from the right-hand side of f of x, which is now dealing with the second branch. That has to be 1 for the limit to exist, right? So then we would say, well, that's how we're going to go and find a. Okay, so in order for the function to be continuous, this limit has to be 1, meaning 2a times x, and x in this case is 1, plus 1 has to be 1. So then 2a plus 1 is 1 minus 1 over a must be 2a is equal to 0 and a must be 0. So in order for this to be continuous, our function is going to have to look like this. 2x squared minus 1 for x is greater than 1. Oh my goodness. I just said that out loud and I realized I switched my plus or minus. This right here got to be greater than 1. So we are approaching from the right. And then this right here is approaching from the left because that's when x is less than 1. Okay, that's my left and my right issues there. Okay, so then it has to be then when a is 0, to that right there must be 1 when x is less than or equal to 1. So, in order for your function to be continuous, a must be 0. Therefore, your function is defined as that. Okay, so here we would say left and right hand limit need to be the same so that there is a limit as x goes to 1, and also that function value at 1 must be the limit. Therefore, we defined it to be 1. So, in summary, how do we check to see if a function is continuous at a point C? 3 conditions, right? So the definition is just the one sentence definition there. Limit as x go to c of f of x must be f of c. But that one loaded sentence means 3 different criteria. First, f of c must be there. there must be a function value at c. There must be a limit as x approaches c. And the limit has to equal to f of c. And that is what it means to be continuous at a point c.